we are going to talk about derivatives of certain functions that, well, maybe we don't have to do a bunch of algebra for. So we're going to talk about some shortcuts that we're going to take so we don't have to do all that stuff that we did every day for the past couple of days. Just a little reminder, if our function is f of x, we define the derivative, or f prime of x, to be the function of this limit, right? So I promise I'm not muted, but we're gonna take the derivative, and we know that it equals this big limit. We'll do a little bit of that today for our test. This is something that you had to know how to solve for and be able to do all the algebra stuff with, okay? Unfortunately, that's a little bit hard. So, and a lot of functions have limits that are a little bit weird and that take a lot of time to find. So what we're going to do today is find a little shortcut for some of these functions, okay? So we're going to start with the easiest function, and we're going to build our way up from there. Okay. I think the easiest function to work with is the constant function, right? The function that is a horizontal line at any point. F of x equals c, where c is a number, okay? What's c in this picture? Oh, you need a note, sorry. What's c in this picture here? 4, good. So c can be any number, and it just represents the height of the graph at a certain point. Okay. So if we want to find the derivative at this point, well, we have the definition. Let's see if we can figure this out, okay? So we have the limit as delta x goes to 0, f of x plus delta x minus f of x over delta x. Okay. All right, so our function now is c, or in this case, 4, right? Let's figure out some of these values. Okay, so if f of x is c, what would f of 1 be? What's f of 1? Four, or in this case, c, right? Since 4 takes place of c, okay? What would f of 5 be? 4 or c, good. What would f of x plus delta x be? C, good. What would f of x be? C, good, for any value x, okay? So looking at my functions in my equation, f of x plus delta x is c, right? Minus f of x is c over delta x. Okay, so I just found what these values are. They're always c with the constant function. Okay. What's c minus c? 0, good. So this is 0 over delta x. And what's 0 divided by anything? 0, good. So this is the limit as delta x goes to 0 of 0. And well, that's going to be 0, right? Okay. So what I did here is I took any constant function, doesn't have to be 4, could be any number, and I found out that the derivative function of that function is 0. Okay. Now, in general, when I take the derivative of any constant c, that derivative is just 0. Okay, so any number, the derivative is 0. Okay. Let's move on to a little bit more complicated function. Let's move on to the identity function. Now, the identity function is the function f of x equals x. It's just that straight line that goes diagonally up. Okay. Let's see if we can find the identity, or, oh, this is identify function. I meant to put identity. Oh my gosh. Identity, not identify function. Okay. Well, we have our limit definition. We have f of x plus delta x minus f of x over delta x. Okay. Well, let's see if we can figure out these values. Okay. If my function is the identity function, which means it maps everything to itself, what is f of x plus delta x? Let's do a few easier examples. If f of x is x, what's f of 1? 1, good. What's f of 2? 2. What's f of star? Star. What's f of x plus delta x? Good, x plus delta x. Okay, so this function takes everything to itself. So this guy, f of x plus delta x, is literally x plus delta x. Okay. All right, what is f of x? X, good. And this is all over delta x. Okay. Looks like we can cross out some x's. So we're left with the limit as delta x goes to 0 of delta x over delta x. Okay. Any way I can simplify this? 1, good. It's the limit as delta x goes to 0 of 1. Well, that limit is just 1. Okay. So with a little bit more work, we've realized that the derivative of just x by itself is equal to 1. Okay. So we have a couple shortcuts now. The derivative of a number is 0. The derivative of x is 1. Okay. Now we can go through the quadratic, the cubic, the quartic using the definition of the derivative. I'm going to save you guys some work, and I'm just going to give you what these derivatives are. Okay. So let's say I want to find the derivative of x squared. Okay. I'm going to give it to you, and we'll try to see if we can come up with a pattern. Okay. So the derivative of x squared is going to be 2x. The derivative of x cubed is 3x squared. And the derivative of x to the 4th is 4x cubed. What's the pattern going on here? Like,
you just drop the power.
So we drop the power up to the front, right? So is that what you said? Is that, yeah. So for example, if I'm taking the derivative of x squared, Blake says, okay, we're going to take the power and drop it up front. So it becomes 2 times x. What happens to the power? Maddie? It decreases by 1, right? So the power becomes the original power minus 1. Okay. And that's basically what happens whenever we have x to any power. Okay. So the derivative of x to any power n is, we're going to take n and move it up to the front. So n comes up front. Okay. And then we take x and subtract the power by 1. Okay. Now, there is a proof for this. It uses the binomial theorem. If you're in discrete math, I recommend trying to prove this, but I'm not going to do that in this class. Okay. I know the power rule looks a little bit weird with this formula. You do have to memorize this. Okay. But if you don't feel like memorizing like the letters or anything, I just want you to know how to find derivatives of power functions. Okay. And it might get a little bit easier as we do a couple more examples. Okay. So let's take a look at this example. We have 3 times x to the 5th. I want to know what the derivative of this function is, and I want to know the derivative at 1, 2. Okay. Let's find f prime of x. Okay. Now, f prime is the derivative. So let's just take the derivative of 3x to the 5th. Okay. Now, I'll talk about this a little bit later, but I think it's kind of common sense that we can take any constant out of the derivative. Okay. So this is the same thing as 3 times the derivative of x to the 5th. Okay. So whenever there's a constant, you can just take the derivative of the power function and multiply it by the constant. Okay. Anyone want to take a guess of what the derivative of x to the 5th is, David?
15x to the 4th.
Not 5. Oh, okay, I see. So 5x to the 4th, and then when you multiply, you get 15. Good. So we took the 5, put it up front, so that went here, and I took the exponent and subtracted 1. So we have x to the 4th. All right, so we're left with 15 x to the 4th. Okay. All right. Second question. Oh, sorry, we didn't finish this question. I have my derivative now. What is f prime of 1? 15, good, because we're just going to plug in 1 to our function. So we're left with 15 times 1 to the 4th, which is 15. Okay. Once we have our derivative, that derivative is going to be a function. Now we can find our second derivative. Now remember, the second derivative is the derivative of the first derivative. Let's see if we can do this. We're going to take the derivative of 15x to the 4th. Okay. So it's going to be, I don't have to write out all the steps here, but it's going to be 15 times the derivative of x to the 4th. What's the derivative of x to the 4th? 4x to the 3rd, good. 15 times 4 is 60x cubed. Okay. I'm going to do one more example and then I'll let you guys on your own. Let's flip to the next page here. Okay. You know what? Yeah, let's just do this one. Okay. We can even do power functions where the exponent looks a little bit crazy. Okay. So here we have x to the 1000th power. I want to find y prime. Okay. Y prime is just the derivative of x to the 1000th power. Anyone want to tell me what this derivative is? Good. 1000 times x to the 1000 minus 1, x to the 999th power. Okay. What's the derivative at 1? Good. 1000 times 1 to the 99 times 1 to, oh my gosh, 1 to the 999. And that's going to be 1000. Okay. Now, practice makes perfect, I think. I want you to try example 3 through 6. Example 6 is on the back. Most of them are pretty easy. Example 5 and 6 are a little tricky. So we'll talk about those, but definitely give these a shot. Now, I haven't done example 5 or 6 yet because I want to go through those a little bit more slowly. But we have some of the easier examples written up. So let's see, example 3, was that Jude who wrote that one up? All right, do you kind of want to take us through your thought process here?
So since we have to do the to 4 or to the 4th power, so we grade out most of the on this 1 in the exponent, that would give us 4 to the 3rd power.
Nice job. Any questions on example 3? Good. Example 3.5, that was Tommy who wrote that one up, right? All right, do you want to take us through your thought process here?
I just did it again for the last answer.
Yeah, perfect. So you took the 3 up front, but you had to multiply it by the 4, and that's why we have 12 here. Nice job. Any questions on 3.5? All right. Example 4, was that Kevin? Do you want to take us through your thought process here?
Just put the 3 up front and then drop the power.
Nice. All right. So I think we're pretty good on doing these simple derivatives. I saw some good answers walking around for example number 5, but I do want to go through this one a little bit more slowly. Okay. When we have an exponent in the denominator, we're still dealing with a power of x. Okay. So let me just go over this real quick. Is there a way to write 1 over x squared as something that isn't a fraction? Troy. Good, right? Negative exponents translates to denominator, right? So whenever you change the sign of the exponent, you're changing it being in the numerator versus the denominator, okay? So essentially, a way to rewrite this fraction is to take it to the -2 power, okay? So essentially what we're doing now is we're taking the derivative of x to the -2. Okay. Using the power rule, it's the same deal except the number's negative. The exponent goes up to the front, so it's -2 times x. The power is subtracted by 1. So the power is going to be -2 minus 1. Okay. What's -2 minus 1? -3, good. So this is essentially my derivative. There's actually a way to write this a little bit better. Anyone want to tell me how to write this more simplified? Troy?
-2 over x.
To the 3rd power. Good. Okay. So whenever you flip the sign of the exponent, it brings something from the numerator to the denominator or the denominator to the numerator. Okay. Any questions on what I did for example 5? All right. We'll do more practice with this, with fractional exponents and negative exponents. But let's keep going. Example number 6, I think, is one of the more tricky sort of situations because we have fractions now. Just a little review. What's another way to write the cube root of x?
X to the 1/3.
X to the 1/3, good. Okay, so remember the cube root, the fourth root, the square root is all a fractional exponent, okay? So if I want to find the derivative of this function, I'm finding the derivative of x to the 1/3, okay? It's the same rule, we're just working with fractions. The exponent goes up front, and we subtract the exponent by 1. Okay, now I'm not very good with dealing with fractions, but let's see if we can try this one. Okay, when I subtract 1/3 by 1, we want to have a common denominator. What's the least common denominator here? 3, right? We want to make everything over 3. Okay, now 1/3 is already something over 3. How do I write 1 as a fraction over 3? 3 over 3, good. Okay, so this becomes 1/3 x to the negative 2/3. Okay. Now I'm kind of fine with this answer. There's a way to kind of simplify this though, right? How can I represent, well, let's deal with the negative first. When I have a negative exponent, we can write that as a fraction, right? So this is technically 1 over x to the 2/3. When you flip the sign, when you change the sign, you flip the line, right? How can I write x to the 2/3 in terms of roots?
Like X to the 2, the square root of 3.
I think I see what you're saying, but the third root of x squared, right? Is that what you meant? Good. Okay. Now I would be fine if you left your answer like this. Weber sign might not be okay if you write your answer like that, but these are other options that look a little bit nicer. Okay. Any questions on example 6? Troy?
So could you multiply those fractions like with 3, x to the 2/3?
Okay, so I think what Troy's saying is, can we do this? 1 over the third root of 3x squared? No.
Like the 3 on the outside.
Oh, so you're saying, okay, can we write it like this? Let me get my pencil here. 1 over 3 third root of x squared. Yeah, you can definitely do this. This is totally fine. That looks a lot nicer than what I wrote there too. All right. Any other questions on example 6? All right. So let's talk about some things we can do with derivatives. Some fun things we can do is, let's say we have a constant, okay? When I multiply a function by c, or a constant number, you can take the c out of the derivative. Now we've kind of already done that, but I think that's kind of self-explanatory there, okay? What I haven't talked about yet is if we have 2 different functions that we can find the derivative of, and they're added together, we can find the derivative of each of the separate parts and just add those derivatives together, okay? Now I know that sounds a little bit weird. Let's just do an example and see what happens. Okay. So we have this big polynomial here. We have 3x to the 5th minus 2x to the 6th and so on. I want to find the derivative, which means that I'm essentially taking the derivative of this whole thing. 3x to the 5th minus 2x to the 6th plus 3x plus 2 over x plus 1. Okay. So using the addition rule, I can split this up into a bunch of things being added, right? So this is essentially saying I can take the derivative of 3x to the 5th. I can take the derivative of 2x to the 6th, the derivative of 3x, the derivative of 2 over x, and the derivative of 1. Okay, and I can add those together. I can find the derivatives of the individual pieces, add them together, and that answer is going to be my derivative. Okay, I think we can do some of these in our heads. What's the derivative of 3x to the 5th? 15x to the 4th. Good, using our power rule. Okay, what about 2x to the 6th? Good, 12x to the 5th. What about the derivative of 3 times x? It's not 3x, but 3, right? Because the derivative of x is 1. One other thing you can do is think of x as x to the 1st. Bringing that power up to the front would give you 1x to the 1 minus 1, which is 1x to the 0, which is 1. Okay. So this derivative is actually just 3. Okay. Let's talk about the derivative of 2 over x. Let's try to make it a little bit simpler. I can definitely bring the 2 out front. Okay, and I'd be left with 1 over x. What's another way to write 1 over x? X to the what power? -1, good. All right, so 1 over x is the same as x to the -1 power. Okay, and what's the derivative of 1? It's the first derivative we talked about. Let's take a look at our constant function, right? The derivative of any number is just going to be 0, right? So the derivative of any number, remember, is 0. Okay. So some things I do want to point out here. The power rule works pretty well. Whenever we have x by itself, you can kind of just remember to just take out the x. It's just the number in front. And the derivative of any constant is 0. Okay. So why don't we go through the negative exponent real quick. Okay. Let me just make sure we're doing good. Okay. What's the derivative of x to the -1st? Good, -x, or -x raised to the -2 power, right? So we're taking the -1, bringing it up front, and subtracting 1 from the exponent. So we get -2 up top. Okay, plus 0 can go away. Okay, this would be fine. Let me just clean this up a little bit. We have 15x to the 4th minus 12x to the 5th plus 3 minus 2. And what's another way to write x to the -2? Yeah, 1 over x squared. So I'm going to put this 2 over x squared. Okay. This is my final derivative. Okay. I know that was kind of a lot. Any questions before we move on? Okay. Did you have a question? Oh, I just saw you. I saw your hand go up. Okay, if you flip over to example 8, we have a very similar type of question. I want you to give this one a try. Try to find the derivative of x, and we'll come back in a tiny bit. Very good job as I've been walking around. Just a little reminder that even though I did a lot of like writing on example 7, you don't have to write the derivative of each of these. Oh gosh, the derivative of each of these steps. It might be helpful in the beginning to kind of do that, and that's totally fine if you want to do it. But if you want to skip from this to this, that's fine with me. Okay. So I got Mason to write up example 8. Do you kind of want to take us through your thought process here?
So I didn't know how to roll for the first and second part where since pi is like almost like a constant, but you don't multiply it, so it's just a number in the front. 2x, you just drop the x. It's x to the 1 minus 1. And then you can take the 5 off the top and then do the normal power rule for x to the -4th power. And then there's the normal power rule.
Nice job. Very good job. Is there anyone who wants to see the derivative of 5 over x to the fourth more with more steps or anything? Okay, it looks like we're all good. Okay. Now, one thing I want to talk about is another way to write your answer. I would take this answer on a test or quiz or anything like that. Some people like to do this. So keep everything the same. And instead of having a negative exponent, we can write our exponent at the bottom. So x to the 5th. Okay, that's also good with me. All right. Okay, let's keep moving on. I think we have a couple more minutes we can do some new stuff with. Okay, now polynomials aren't the end, right? There's more functions than just polynomials. And we're going to start talking about derivatives of those type of weird functions as well. The first one I want to focus on is the natural exponential function. And the natural exponential function is just e to the x. Okay, so f of x equals e to the x. There is a proof for this derivative, but I honestly don't really want to go through that proof. It's a very long. So I'm just going to give you what this derivative is. Okay, if I take the derivative of e to the x, it's just e to the x. Okay, so the derivative of e to the x is itself. You do have to know this, memorize. Okay. Another one I want you to memorize is the derivative of any exponential function. Now, the basic gist of any exponential function is a constant raised to any power x, right? So if I want to take the derivative of any power or any number raised to a power of x, the derivative is ln of the base, the natural log of the base, times that exponential power. Okay, I think it is easier to look at this when we do an example. Just to get our feet wet here, let's find the derivative of 5 to the x. Okay. Now, what's my base here? What is a? A is 5, good. So can someone tell me, using the formula, what the derivative of this function is?
Natural log of 5 times 5 to the x power.
Good, natural log of 5 times 5 to the x. You literally just plug it in to the formula. Okay. Let's go to our next page here. Okay. So now we're getting a little bit more funky. We have a big string of numbers here. We have e to the x, we have 2 to the x, 4 to the x squared, and 1500. Okay, let's see if we can find the derivative of this one here. Okay, well, I can take the derivative of each of the pieces and add them together. Okay, so I have 2 times e to the x. If I want to take the derivative of this, I'm just going to take 2 out of the derivative. So 2 times the derivative, oh my gosh, of e to the x, right? So is there anyone who can tell me what the derivative of 2 times e to the x is? What's the derivative of e to the x? Yeah, I think I heard it. So it's going to be 2 times the derivative of e to the x, which is just itself. So 2 times e to the x. Does that kind of make sense? Good. Okay, we're going to add on the derivative of 2 to the x, this guy here. Using the formula, what's the derivative of 2 to the x?
Natural log times 2 times 2 to the x.
Good, natural log of 2 times 2 to the x. Okay, let's do the derivative of 4x squared. What's this derivative? Use the power rule.
Next to the
8x to the first power, good. And finally, what's the derivative of 1500? 0, good. The derivative of any constant is 0. Okay. So this is fine. Let me just clean it up a little bit. 2e to the x plus the natural log of 2 times 2 to the x plus 8x. Oh, plus. That's my derivative. Any questions? Okay. I'm going to give you like 1 minute to try example 11. Kind of the same deal, a bunch of different derivatives strung up together. Okay, we're kind of running out of time here, so let me just go through this one real quick. Okay, we just want to find the derivative of all the different parts, right? What's the derivative of 7 to the x power? Good, just using the formula, right? Okay. What's the derivative of 1/3 e to the x? Good, 1/3 e to the x, right? So the derivative of e to the x is just itself. What's the derivative of x to the 500?
500x to the 499th power.
Good, using just the power rule. And what's the derivative of pi? Pi is a constant. I think I heard it, James. Good. The derivative of any constant is 0. Okay, so pi, I know it looks kind of weird, but it is a number. Cleaning this up a little bit, we have ln of 7 times 7 to the x plus 1/3 e to the x plus 500 x to the 499th power. Okay. Any questions? I am very proud of myself. I figured out how to make one class worth a set of provided notes. But that's all I have for today. We do have a quiz review though. So I'm gonna pass this out. Same thing goes with the previous weeks. What I'm gonna do is I'll post the answers to this on my classes later today. If you have somewhere to be, feel free to leave.